welcome to another video of calculus. Today we will discuss some examples on limit, and after that we will see the bounded sequence. So the first example is, use the definition of limit. Use the definition of limit to find. Use the definition of limit of a sequence. Limit definition of use the definition of limit of a sequence to show that limit n tends to infinity, 1 upon square root of n plus 7 is equals to 0. Use the definition of limit to show that limit n tends to infinity 1 upon square root of n plus 7 is equals to 0. So here, like previous examples, we have xn is equals to sequence xn is equals to 1 upon square root of n plus 7, and we have to prove this limit of this sequence is equals to 0. We know that the definition of limit of a sequence, we just have to find the number k such that is to find the positive number k such that mod of xn minus l is less than epsilon for all n greater equal k. We have to just find this number k for which mod of xn minus l 0 is less than epsilon. Now we will consider mod of xn minus limit is 0 is less than epsilon. If this n greater equal k, then we can write this mod of xn minus 0 is less than epsilon. Mod of xn minus 0 means xn, the value of xn is 1 upon square root of n plus 7 minus 0. Now here we get mod of 1 upon square root of n plus 7, and this is, we can write this directly, 1 upon square root of n plus 7. If this will become minus, then modulus of minus sign is plus. So 1 upon square root of n plus 7, and clearly we know that this 1 upon square root of n plus 1, as this n plus 7 is greater than n plus 7 is greater than 1, n plus 7 is greater than n. If here we are adding 7 to n, so this n plus 7 is obviously greater than n. Now if we take the square root, then square root of n plus 7 is obviously greater than square root of n. We will taking the positive square root. After reciprocal, we can write the square root of n plus 7, 1 upon square root of n plus 7 is less than. If you take the reciprocal, then inequality changes, square root of 7. So we can write this mod of xn minus 0, which is equals to 1 upon this root n plus 7 is clearly less than 1 upon root n. It's clearly less than 1 upon root n, and we are taking here n greater equal k, so this is less than epsilon. This is again less than epsilon. So here we get 1 upon square root of n is less than epsilon. We have to find the value of n greater equal k. So we are just looking to find the value of k. So if we rearrange this, then we get this square root of n is greater than 1 upon epsilon. So if we take the square on both sides, then we get n is greater than 1 upon epsilon square. So here n is greater than 1 upon epsilon square. Now if we choose the k is equals to 1 upon epsilon square, then we get k is equals to 1 upon epsilon square. Here square root of n is equals to this. So if we square on both sides, then we get this 1 upon epsilon. Now we have to find the value of n greater than k. So here 1 upon square root of n is less than epsilon, implies the square root of n is greater than 1 upon epsilon. Now if we square on both sides, then we get n is equals to 1 upon epsilon square. Therefore we get, for given epsilon positive, there exists k is equals to 1 upon epsilon square, such that mod of xn minus 0 is less than epsilon for all n greater equal this k. Hence limit n tends to infinity, that is the limit of the sequence. Sequence was 1 upon square root of n plus 7 is equals to 0, because for that L is equals to 0, we get the value of k, which is equals to 1 upon epsilon square. So, this limit is 0. Now, the next example is discuss the convergence. This is the one new example. Discuss the convergence. Discuss the convergence of the sequence. Discuss the convergence of the sequence. Minus 1 raised to n into n divided by n plus 1. Minus 1 raised to n into n divided by n plus 1. Now, we have to discuss the convergence, either this is sequence convergent or divergent. Here we have given x n is equals to minus 1 raised to n into n divided by n plus 1. That is, we have to find this limit n tends to infinity, x n exists or not. Now, the limit n tends to infinity, x n is, here x n is given minus 1 raised to n into n divided by n plus 1. Now, if we take n common from the denominator, we can write this limit n tends to infinity minus 1 raised to n into n. If we take the n common, then we get 1 plus 1 by n. Now, here n gets cancelled, the remaining terms are limit n tends to infinity minus 1 raised to n upon 1 plus 1 by n. Now, if you put limit n tends to infinity minus 1 raised to infinity upon 1 plus 1 upon infinity is 0. So, this will become just minus 1 raised to n. Now, there are two possibilities, either minus, if n is even, then we get 1, and if n is odd, then we get minus 1. So, there are two possibilities here, minus 1 whenever n is odd number and 1 if our n is even number. Then there are two possibilities, limit n tends to infinity will become 1 upon infinity will become 0. So, 1 plus 0 is 1. So, denominator vanishes, then minus 1 raised to n, there are two possibilities, minus 1 and 1. So, hence there are two possibilities, minus 1 and 1. So, limit does not exist, hence limit of a sequence does not exist. Limit of a sequence does not exist, hence this sequence is not convergent. Therefore, this sequence minus 1 raised to n into n upon n plus 1 does not converge. Does not converge. If you have given problem is in this form, discuss the convergence, you will just check the limit. Otherwise, if the question is of the form show that this limit, then we will find the value of k. Now, we will see the next topic, which is the definition of bounded sequence or some theorems on limit. Next definition is definition of bounded sequence. Definition of bounded sequence. A sequence xn, is said to be bounded. Sequence of real numbers is said to be bounded if there exists a real number, m greater than 0, if there exists a positive real number m such that all the terms of that sequence mod xn is less than or equals to that m. Mod of xn is less equal m for all n belongs to natural number. If the all elements of the sequence, modulus of all the elements of the sequence is less than or equals to that this number m, a particular number m, then we will say that the given sequence is bounded. So, this is the definition of bounded sequence. For example, if we take sequence xn is equals to minus 1 raised to n, then the terms of this sequence are minus 1, 1, minus 1, 1, and so on, minus 1, 1. If we take the modulus of this sequence xn, which is clearly 1, modulus of minus 1, again 1, modulus of 1 is 1. So if we take m is equals to 1, then all the terms of this sequence are less than or equals to 1. So here mod of 1 is less than or equals to 1, hence it is, this sequence is bounded, xn is bounded. This is the definition of bounded sequence. Now we will see one theorem on this bounded sequence. The important theorem is, this is the important result. Every convergent sequence, convergent means whose limit exists, every convergent sequence, every convergent sequence of real numbers, every convergent sequence of real numbers is bounded. Every convergent sequence of real number is bounded. This is the important result in this second chapter. To prove this theorem, we have given that xn is convergent sequence and we have to prove that that sequence is bounded. Now we suppose xn is a convergent sequence, which converges to, suppose, limit L, convergent sequence which converges to limit L. Therefore, now this sequence xn is convergent and converges to L means limit n tends to infinity, xn is equals to L, by definition of convergence of the sequence. Now by using epsilon delta definition, therefore by definition of limit of a sequence, we can write for all epsilon positive there exists some k belongs to natural number such that mod of xn minus L is less than, such that mod of xn minus L is less than epsilon for all n greater equal k. Now here this limit exists, sequence is convergent means this limit exists. So if limit exists, then for all epsilon positive we can find the number k such that mod of xn minus L is less than epsilon. Now if we take epsilon is equals to 1, for epsilon is equals to 1, there is again one number k greater than 0 such that mod of xn minus L is less than that epsilon. Here epsilon is equals to just 1. So for all n greater equal k, we can write for every epsilon. Now if we take the particular epsilon is equals to k, then we can write mod of xn minus L is less than 1 for all n greater equal k. Now we can write, now consider mod of xn. We have to prove that this convergent sequence is bounded. Till now we have just write this sequence is convergent and converges to this limit L. Now as this limit exists, that is the sequence is convergent, just using the definition of limit of sequence we will get this mod of xn minus 1 is less than 1. Now we have to prove that this sequence is this sequence is bounded. To prove any sequence is bounded, we have to prove that mod of xn is less than or equals to m for all n belongs to natural number. Every element of that sequence, we take the modulus of every element of that sequence, then that modulus must be less than or equals to some m. Now we will take the mod of xn. Now mod of xn, we can write this mod of xn is equals to xn minus L plus L, just adding and subtracting L, there is no difference. So now we can use the triangle inequality, mod of xn minus L plus L. So xn minus L is equals to A and L is equals to B. We can write mod A plus B is less equal mod A plus mod B. Now this mod of xn minus L is strictly less than 1. So we can write this 1 plus mod L, 1 plus mod L. So here clearly we can write mod of xn is less than some number. L is the limit of the sequence and just adding the 1 on that limit. If we just put here epsilon as it is, then we can write epsilon plus mod L. So for a particular epsilon we can find a particular m. So mod of xn is less than 1 plus mod L. So here clearly we can say that every element of sequence xn is strictly less than 1 plus mod L, but we have to prove that mod of xn is less than or equals to m. If this element 1 plus mod L is itself the element of xn, then we can write this xn is less than or equals to, but here we get mod of xn is strictly less than. So if we choose the maximum number, that is if we find all the elements of xn and get the maximum number from that sequence, we can take that element as m, or this 1 plus mod L is element of this xn, and we can write this 1 plus mod L is equals to m, for which all the elements of sequence xn are either less than or equals to that m. Thus if we set, now we will choose m is equals to maximum number among all these mod of x1, mod of x2 up to mod of xn, suppose xk minus 1, comma mod of 1 plus mod L, 1 plus mod L. Here this 1 plus mod L, all the elements of the sequence xn for which n greater equal k, for all the elements of xn n greater than or equals to k, we get mod of n minus L. So now just in detail we will take here xn is equal, if xn is equal to this x1 x2 up to suppose xn, then suppose xk plus 1 xk plus 2, then all the elements of this sequence. Now by definition of limit we can say that for all n greater than or equals to k, so these elements all n greater than or equals to k means xn, for all n greater equal k means xk plus 1 xk plus 2, all the elements are very close to L, but there is no condition on this x1 x2 up to xk minus 1. So if we choose the maximum number of mod of x1 mod of x2 up to mod of xk minus 1 or L plus mod L, then we get mod of xn is less than or equals to m. Then we can write mod of xn is less equal n for all n belongs to set of natural numbers. Here in mod of xn is less than 1 plus mod L is for only those n for which n is greater than or equals to k. So that definition says that xk plus 1 xk plus 2 and all these elements are very close to L. From that we can write mod of xn is less than or equals to 1 plus mod L. But if x1 x2 x3 any number from these k minus 1 numbers is greater than this 1 plus mod L, then we have to choose that m, because we need for all n belongs to natural numbers xn is less equal m. So we choose the maximum between these two numbers. There is no need to write this in the proof. So mod of xn is less equal m for all n belongs to natural number. This is the definition of bounded sequence. This implies sequence xn is bounded, or every convergent sequence is bounded. Every convergent sequence is bounded. Every convergent sequence is bounded. Hence the proof of this theorem. Now the next is sum, difference, product and quotient of the sequences. This is another theorem. There is no need to prove this. Sum, difference, product. If let xn comma yn be sequences of real numbers such that xn converges to x, suppose this xn converges to x and this yn sequence xn sequence xn converges to x and this yn converges to y, then addition of xn and yn, that is sequence xn plus sequence yn converges to x plus y. Again the product, that is x into y, xn into yn converges to x into y. Also x minus y converges to x minus y, and quotient, that is xn upon sequence xn upon sequence yn converges to x upon y, where yn is non-zero and y is also non-zero, where given that this y is non-zero. Also this is suppose first one, this is second one, this is third, fourth. xn minus yn is also converges to x minus y, xn minus y converges to x minus y. Also if you have given that suppose c into some x1, some c is constant number into some sequence xn, this sequence is again converges to c into x. So these are some topics. If you have given xn and yn, also their limits x and y, then addition of the sequences converges to addition of the limit. Similarly, subtraction of the sequences converges to subtraction of the limit. Multiplication of the sequences converges to their multiplication of the limit. Also for the division, there is no proper theorem on the division. There is no need to write this third one. Suppose this is third and this is fourth. So these four results are in general true, fourth one is not in general true, this is not in general true. So these are four results: addition, subtraction, multiplication, and multiplication by some constant number is also convergence to the multiplication of constant by limit or addition and subtraction of the limits. Hence the theorem, there is no need to prove this result.